more parameters of that equation. In that case, we say equation is over-identified. Let's say just now, let's say for example equation 1. If equation 1, if let's say there are more than one possible estimate for value 0 and value 1, then we call that over-identified. Okay, but indirect square can only be used to estimate exactly identified equation. Okay, so meaning that this one is exactly identified. Okay, so there are three possible outcomes. So let's say we have a simultaneous equation, and then we want to estimate parameters for each of the equation. So whether or not we are able to estimate depends on the types or the category of the equation. So there are three possible outcomes: whether we can get a unique estimate of the parameters in this equation, the one we call as exactly identified equation. If we cannot get estimate, there is no, it is impossible to get estimate because it's under-identified. But if we can get estimate, but there are more than one possible values for each of the option. The one we call as over-identified equation. Okay. So indirect square can be used only for the case of exactly identified. So over-identified we cannot use ILS. We have to use alternative way. So again, sometimes it can happen that there is more than one numerical value for one or more parameters of the equation. In that case, we say that the equation is over-identified, and there is nothing we can do about under-identification, assuming the model is correct. So for under-identified equation, we cannot get estimate. We can do nothing. If an equation is exactly identified, we can use the method of indirect square, the one that we discussed just now, to estimate parameters. If an equation is over-identified, then indirect square will not provide unique estimate of the parameters. But fortunately, we have alternative method. Okay, fortunately, we can use the method of two-stage least square, 2SLS, to estimate the parameters of an over-identified equation. There is a systematic way to determine whether an equation is under-identified, exactly identified, or over-identified. So, if you have the equation, the simultaneous equation, so you have to identify first whether each of the equation can be estimated, the parameters within or inside or within that equation can be estimated or not. So you have to identify first whether the parameters of coefficient can be estimated or not. The method of reduced form regression to determine identification is rather cumbersome, especially if the model contains several equations. So imagine that if we have four endogenous variables, for example, and then you have four reduced form equations. So meaning it's quite tedious to do the calculation. Okay, so you can. Fortunately, so this one actually the model contains several equations. Okay, fortunately the two-stage least square method can also be used to estimate parameters of the exactly identified equation. So here in this lecture we have two different ways of estimation: the indirect square (ILS) and the two-stage least square. Okay, so indirect square can be used to estimate for the exactly identified equation. Two-stage least square can be used to estimate for exactly identified as well as over-identified. Okay, so IS cannot be used to estimate, indirect square cannot be used to estimate for the case of exactly identified. Exactly identified cannot. So exactly can only be exactly identified. The ILS can be used to estimate this. Okay, but ILS cannot be used to estimate over-identified. Okay. Two-stage least square can be used to estimate for exactly identified as well as over-identified. Yeah. So now, rules for identification. The order condition of identification. To understand the so-called order condition of identification, we introduce the point notation. number of endogenous or jointly dependent variable in the model. So you refer to the example 1. So we have two, right? We have CT and YT, our endogenous variable. CT and YT both are endogenous variables, so M equal to 2 lah. Number of endogenous for the given example. Okay, M number of endogenous variable or dependent variable in the model. And K number of variables excluded from equation under consideration. So K number of variable doesn't matter whether endogenous or exogenous or both. Number of variable excluded. So out of the total variable exists or appears in the system of entities under the equation, then we look at for each of the equation how many variables excluded. Okay, that's our K. Okay. So then you have to identify each of the equation whether it is exactly identified, over identified, or under identified. So it is exactly identified if K equal to M minus 1. So M for the first example, our M minus 1 equal to what? 2 minus 1 lah. 2 minus 1, 1, M minus 1. The first example lah. So because we have two endogenous variable, YT and CT. So M equal to 2, 2 minus 1 equal to 1. Okay. So K number of variable excluded. So K number of excluded for that particular equation lah. So you have to identify. So if K equal to M minus 1, then the equation is exactly identified. So that you can use which technique to estimate? Linear direct square, and you also can use two-stage square. Both lah. Okay. You can use ILS direct square, as two-stage square. If K greater than M minus 1, then equation is over identified. Over identified means that each of the coefficient has more than one possible value. So we cannot use indirect square because indirect square can only be used for the case of unique estimate as is. But this one is over identified, so you only able to get estimate using two-stage square. Okay, two-stage square. So if K less than M minus 1, let's say that particular equation has all variables. So all variables mean that there is no variable excluded. So K equal to 0. So less than M minus 1, then the equation is unidentified. So meaning that for that particular equation, then we cannot get estimate. So don't try to find, you will not get the estimate. Even you try to use indirect square, you estimate that let's say you identify the reduced form equation, and then you estimate reduced form equation, and you try to solve in order to get estimate, you will not get. Okay, you will not get estimate because there is no possible estimate. Okay, for that under identified equation. So don't waste your time. So you have to identify first whether you are able. So you need to identify the equation whether it is exactly identified, over identified, or under identified. If under identified, then don't waste your time. You will not get estimate. Okay. If it is exactly identified, you can either use ILS or two-stage square. If it is over identified, then you can get estimate using two-stage square only. Okay, two-stage square only, you can use ILS. So example, consider again the Keynesian model of income with dimension given by equation 1 and 2. So equation 2 we do not need to estimate because it has no parameters, there is no coefficient to estimate. So now we want to know whether the first equation we can get estimate or not. Okay. So before you try to get estimate, you need to identify first using the order of identification, identify whether it can be the parameters or the coefficient can be estimated or not. So here you identify that out of for the whole system of equation, so we have how many variables we have? We have C, we have Y, and we have I. So we have in total we have 3 variables in all equations. Okay. In all equations we have 3 variables, that is CT, YT, and IT. Out of the 3 variables, 2 of them are endogenous. Okay, out of the three, two are endogenous, which is CT and YT, so M equal to 2. Okay, M equal to 2 because only two of them are endogenous. IT is exogenous. IT exogenous. Okay. For the first equation, how many variables excluded? We have C, we have Y, but we don't have I. Okay. The first equation we have C, we have Y, but we don't have I here in the first equation. So there is one variable excluded. K equals 1. Understand? So we have three variables in total. For the first equation, we only have two, C and Y. We don't have I here. So for the first equation, K equals 1, variable excluded from the equation. K equals 1, and then you identify M minus 1 equals what? M 2. 2 minus 1, 1. So this K1 equal to M minus 1. So it is exactly identified. Okay. So indirect least square method can be used to estimate parameters in the first equation. In addition, you also can use, because exactly identified, you also can use to statistic square also can be used. Okay. Alright, estimation of n over identified equation, the method of two statistic square. So this is the second approach using two statistic square. So in addition to the indirect square. To illustrate the method of two statistic square, 2SLS, consider the following model. So let's say we have two equations. Again, it's multi-line equation. So our endogenous variable are YT and MT. Okay, because MT influence YT, YT influence MT. Okay, so YT and MT are our endogenous variable in the system. Okay, state of equation. So here we have YT income, MT stock money, IT investment expenditure, GT government expenditure on goods and services. So this one the item, U1, U1 and U2. So in this model, the variables I and G are assumed exogenous. Okay, so I and G are exogenous. YT and MT endogenous. YT, MT endogenous, I, G exogenous. Okay. So here, how many total variables we have? In total, we have the total variable we have in the system. We have YT, MT, IT, DT. So we have 4. Right. So now we want to know each of the coefficient in the first equation, second equation, A0, A1, A2, A3, and the second equation whether 0, whether 1, whether we can get estimate or not. Okay, we want to identify. So we have to identify each by, for each by each of the equation. Okay, so now your M equal to 2, right? M 2. So M minus 1, 1. So the first equation, your K equal to what? For the first equation, now we want to know whether we can get estimate or not for A0, A1, A2, A3. Are we able to get estimate of this coefficient? So now M minus 1, 1. How about K? K equal to what? K equal to, how many variables excluded? 0. Because it has all variables there. Okay. So, in total, the variable that we have in the system, we have Y, M, I, G. The first equation has all. Okay. So there is 0 variable excluded from first equation. So K equal to 0 less than M minus 1. 0 less than 1. 0 less than 1. So it is under identified. So we cannot get estimate. The first equation we cannot estimate. Okay. It is under identified. So we are impossible to get estimate of the A0, A1, A2, A3. How about second equation? M same lah. M equal to 2 minus 1, 1. K 2. Because we don't have I, we don't have G. Okay. So k equal to 2. So 2 greater than 1. 2 greater than 1. So it is over identified. Huh? It is over identified. So over identified means that we can only get estimate using two-stage square. We cannot use IS because IS can only be used for exactly identified. Yeah. So obviously we have a simultaneity problem here because of the feedback between income and money supply. Applying the order condition of identification, we can check that the income equation is unidentified because it has no variable in the model, whereas the money supply function is over-identified. The second equation, the first equation is unidentified. Second equation over-identified because it excludes two variables in the system. Note that m equal to 2 in this model. Okay, so that k greater than m minus 1. K equal to greater than 1. Since the income equation, the first equation is unidentified, there is nothing we can do to estimate parameters. In the case of money supply function, if we use indirect least square to estimate parameter, we will not obtain unique estimate of for the parameters. Actually, beta 1 will have two values. If we use ordinary least square because of the likely correlation between income and the stochastic error term, or else estimate will be inconsistent. Suppose in the money supply function we find a surrogate or proxy or an instrumental variable for yt, such that although resembling yt is uncorrelated with ut, so if we can find such a proxy, ordinary square can be used straightforwardly to estimate the parameters of the money supply function. So to obtain such a proxy or instrumental variable, we can use the method of two-stage square. The method involves two successive application of ordinary square. So it has two steps. So we use ordinary square, but we do not directly estimate. So we have to use the involve two-stage. Okay. So now for this given example, we cannot estimate this one, but we can estimate the second equation. Okay. So now the two-stage square procedure, what we need to do, you cannot regress MT against YT directly because YT and MT are endogenous. So YT correlated with the error term. So you cannot use ordinary square to regress MT or YT. So what you need to do, you need to find alternative. You need to find what we call as a proxy for YT. So I call as instrumental variables for YT. So it involves it involves two steps. The first step, we need to get what we call that fitted value of y. Okay, fitted value of y, so that we can use that fitted value to replace this in the equation. Instead of using YT, we need to use alternative variable, we call it instrumental variable or proxy for YT to replace YT, so that that one we need to make sure that the replace variable must be free or not correlated with the error term. Okay. So one possible way is by using the fitted value of y. Okay, fitted value of y instead of y. So that the first step, so it involves two steps, two-stage square. The first stage, we need to get the first stage is to get the replacement of YT by estimating the fitted value of y. Okay, the first stage. Second stage, then we can use the fitted value of y to estimate the model. So MT regress against the fitted value of y. Okay. So stage 1, to get rid of the likely correlation between income and the error term, first regress YT on all predetermined exogenous variable. So this one, regress YT. So here, the second equation, we cannot use YT, but we need to find alternative. We need to find the replacement for YT. Okay, that can be done by using y hat or fitted values of y hat. But to get y hat, we need to regress y against other variables. other variables. Okay, so regress yt against all of the endogenous variable only. Endogenous variable not only that come from this equation, but also come from the entire for the entire equation for the system of the simultaneous equation. So endogenous variable we have ing just now. Ing our endogenous. So you have to regress y against ing to get fitted value of y, and then second stage use the fitted value of y to regress this model, this equation. So that two stages. So again, to get rid of the likely correlation between income and error, first regress yt on all predetermined or endogenous variable in the whole model, not just on that equation only, not just on that equation. In the present case, this means regressing y on the predetermined variables I and g as follows. So you regress y against I and g in order to get y hat. Okay, because we cannot use y, we have to replace. In the second equation, we have to replace y with something else. So that can be done by using y hat. Okay, so because y hat is not correlated with the error, so because this one yt is correlated with the error term, so we cannot directly use y, so we have to use fitted value of y, because fitted value of y is not correlated with the error term. Okay. So from equation 8, we obtain the estimate. So we get y hat after we regress the y against all endogenous variable, you get y hat. And then, so where y hat is the estimated mean value of y given the value of I and g, the endogenous variable. Therefore, we can write equation 8 as this. So y equal to, so equation 8 as one. So we can rewrite equation 8 equal to fitted value plus the error term. Following the already squared theory, the fitted value of y and ability are therefore uncorrelated. Okay. So stage 2, the over, after you get the y hat, the fitted value of y, then you can use that to estimate that equation. Okay, the equation 2, but do not use y, but use fitted value of y. Okay. So second stage, stage 2, the over identified money supply function can be written as this. Okay, so you can regress m again against the fitted values. So where we have new term like this. So comparing equation 11 and 7, we see that they are very similar in appearance. The only difference being that yt is now replaced by fitted value of y hat. It can be shown that although yt in the original money supply function is likely to be correlated with the stochastic error term, hence rendering on an already squared inappropriate, the fitted value of y hat in equation 11 is uncorrelated with the vt, asymptotically, that is, and last sample, or more accurately, as the sample size increases indefinitely. Okay. As a result, already squared can now be applied to equation 11, which will give a consistent estimate of the parameters of the money supply function given by equation 7. So consider the example. So the given, the same example. So now let us continue with the money supply and income model of equation 6 and 7. Equation 6 and 7, this one. 6 and 7. But we know that the first equation we cannot get estimate. We only able to get estimate of this. But since it's over identified, we cannot use generic square. Since it's over identified, we cannot use INS. We have to use two states the square. So two states the square requires us to get the fitted value of this, so that we use fitted value instead of the original series. Okay. So let us continue with the money supply and income model of equation 6 and 7. The abuse file give data on YT incomes as measured by GDP, MT money supply as measured by the M2 measure of money supply, IT investment as measured by gross private domestic investment, GDPI and GT federal government expenditure. The data are in US dollar. So example 4 is one. Example 4. So now we want to use the two-stage least square, but unfortunately we cannot estimate the first equation. We are only able to estimate second equation. So in order to estimate second equation, the first step, the first stage, you have to get y hat. How to get y hat? You have to regress y against all the exogenous variables. All exogenous variables. So you go to quick estimate equation. So you have your now y, the y, because you want to get theta value of y, so y regress against exogenous variables. So we have ing. So C for the constant, so then ing. Okay, so you get this one. So this one you can interpret as usual. You want to interpret. So interpret this result in the usual manner. Notice that all coefficients are significant at that 6% level. If 6%, if 5%, only one. They were significant. So now after you estimate the one, you need to get the theta value. You go to view actual theta ratio table. Okay, so these are our theta value. So you need to copy this one, this theta value, copy. Okay, and then you create new object, new object. New object, series. So let's say you name that as y hat. Okay, theta value, let's say you name, it's up to you lah, whatever name you want to use. Let's say we just put y hat. Okay, so you open this one, y hat, you paste. So you click edit, you paste the theta value just now. Okay, so you close. Now we have our what we call like instrumental variable proxy for y. So y hat is proxy, which is now no longer it's not correlated with the error term. Okay, y is correlated with error term, but y hat is not. So that's the first step. So we already have y hat. Now second step, the stage 2. Then stage 2 you can regress. Stage 2 you can regress the equation. This one, but instead of using y, use y hat. Yeah. So you go to quick estimate equation. So we have m space c space y hat. this is stage 2. Stage 2, you regress using already square and regress against the y hat in order to get estimate for the second equation. Okay. Okay, this one is the equation 1. So you get estimate lah. So this is estimate for. So equation 2, we have beta 0, and then this give the estimate for beta 1, beta 0, beta 1. Equation 7, equation 7. So in if-use, you do not need to do the two-step because it allows us to get estimate directly. That can be done if you estimate using two-stage square. So you go to just like usual quick estimate equation, and then you just put the model that you want to estimate, which is m space c space y, not y hat. The second equation, because we want to regress money supply against income. So you put m space c space y, and then you select method, you select t as ls, two stage square. Okay, so you get this one. So this is model one estimate, but you need to put all the list of instrumental variable. That is the list of our exogenous variable. So here our exogenous variable I and g, right? So you can just put I and g, exogenous variable. Okay, and then just okay. Okay, this one is the next question. So you compare. So this is we obtain using if-use, using two-stage square. Just now when we do it manually, step by step, the two stage. So we get this. Okay, this one the previous one. So this one using if-use. So exactly the same estimate, by different p-value. So the one that we estimated before, because we use y hat, but this one, okay, so maybe use different way to estimate the p-value. Okay, so perhaps this one more reliable in terms of p-value. The estimate is exactly the same. The estimate of the parameter is exactly the same. So if you regress, you simply regress with m against y, you get this one and the square, so which is not correct and this one is correct. So using if-use, we get this one. Comparing the two-stage square and the square result, you might see that results are not vastly different. This may be so in the present case, but there is no guarantee that in this way, this always will be the case. So besides, we know that in theory, two-stage square is better than the square, especially in last sample. If, for the case of simultaneous equation, if there is no simultaneous IT, then it's better to use another square. If there is no feedback, okay, just one equation, then it's better to use 100 square. 100 square is more efficient estimate as efficient estimator. But when there is feedback, there is a simultaneity problem in the system, then it's better to use 2 state square to SS over 100 square. Now, try to use the same method to 2 state square for the first example. The earlier example, equation 2. Sorry, example 2. Example 2, which is represent the first. This one indirectly square, this one indirectly square. So we want to estimate. The first equation. Okay, this one. Based on the order of identification. In total, we have how many variables? 1, 2, 3. So the first, m equal to 2. 2 as endogenous. So m minus 1, 1 lah. So the first equation, how many k equal what? 1. So this one exactly. This one I think we have mentioned before. This is exactly identified. But you can use INS as well as 2 state square. You can use both. Okay. So just now we use indirect square to solve it. But now try to use the 2 state square. This one, the first equation just now. How to use 2 state square? You have to estimate model. This one second or person? Consumption, investment, and person. So you go to quick estimate equation. So C. Okay, this one is consumption. C and income. Select 2 state square. What do you need to put here? What we should put here? Investment. Okay, so put the endogenous variable as our instrument. To calculate or to get the instrumental variables. So if you do this, okay. So you get the same estimate that we calculate using direct square. We have 35 point, the intercept, and then 0.81 for the slope. Okay. So for the manual approach, if you want to do step by step, then I leave it to you to do. You should have to get the same estimate. Okay, try to do it later on. During the 30-minute break, you can do the 2-step manually using only square. Okay, you should be able to get the same. Alright, 30 minutes break. So later we do another example. We only have one data for the last question. So maybe less than 30 minutes we can finish it. Okay, so we continue lecture. We do lecture at 7:55. 30 minutes. So 7:50.